complex ways. And and then you can apply that to more complicated geometry. So for the first example, this is our 2D subduction zone problem. So we're going to have a continental crust here, continental mantle. We'll have oceanic crust, that's your slab going down, then oceanic mantle. So the surfaces that we'll be putting in include the topography and bathymetry right up here along the top. We're going to have the subduction interface coming down here, and a portion of that for the problems that this is set up for would have a co-seismic region, which would be set up as a different node set from the remainder of the subduction interface. And then we're going to actually, yes?
If you need a pointer,
What's that?
If you need the pointer, you need to click on that arrow up there in the next to draw.
I did. It doesn't seem to work.
Oh.
Because it just stays that no matter what. Yeah, I tried that. Oh, wait, no, it came back.
I clicked. There, you got it.
Oh, because it never worked for me.
Can you move it?
Now, I can't move it.
Oh. Now, what happens if you do it now?
Let's see. It came back.
I think just click on different places.
Oh, okay. I see. All right. So anyway, there's our co-seismic region. And then we have the bottom of the slab, which is actually just, for this simple problem, we just offset the subduction interface to create the bottom of our slab. Let's see. So I think I might just go directly to the 2D problem before I talk about the rest, because, yeah, we don't need that right now. So let me get Qubit up here. Okay, is Qubit showing up there?
Yep.
Okay. All right, so this first example, Brad showed you briefly some of the features of Qubit earlier. So the first thing I'm going to do is set my directory so it's set to the proper location for the problem that we're working on. It's being slow. Okay, so let's see which one. Let's do that one. Yep. So we've set it to the proper directory. We're going to open up the journal, the main controlling journal file for this problem, first of all, just so we can. And what you can see in this journal file, the first thing we do is we play back the geometry journal file. So I'll open up the geometry journal file. So this problem, we use the ApRepro scripting language that Qubit provides. So the first thing that we're doing here is we're setting the units to SI units. And so what this allows us to do is to give coordinates and things like that where we don't have to do everything in SI by itself. We can tell it that it's kilometers, and Qubit will automatically translate it for us. So we'll do that and the reset, which we pretty much do at the beginning of every problem to get rid of everything that you had before. So That gives us a bunch of variables that are now defined in the editor, the FFO editor here. We're going to turn undo off. And then what we're going to do is we're going to start defining vertices that are going to create our curves. And what you'll notice is that some of the vertices, we will actually save the vertex ID as a variable. And what that allows us to do is to refer to specific vertices later on. That we can do that either when we need to start or begin a curve, or if we need to split a curve at a particular vertex. FRPro gives you this ID vertex, which will give you the ID number of the vertex that was just created. So that's the first thing we're going to do, create this vertex at minus 600 kilometers and then minus 2,000 meters. And then we'll get an ID for it. So if we look in our editor here, we've created our vertex. And there's the ID that it was the first vertex created, so it will have an ID of 1. We'll create some more vertices here and then get another ID right down here. And then we'll go all the way here to the end. So we're going to create, oops. So now we've created a whole sequence of vertices, and this is forming our topography and bathymetry. So it's just a set of points. And then what we're going to do is we're going to form those together into a spline curve. And we do it by saying, saying vertex number, and then we give it the first one that we created to the last one that we created. And we'll form those all together into a spline curve, and then we'll get the ID of that curve and call that topography. So that'll be our topography bathymetry. Okay, there's our spline curve. That's the top of our model. Now we're going to do something similar. We're going to create a curve that represents the slab interface, the subduction thrust interface. We're going to do a similar thing. We'll form this first vertex here, get the ID number of it. We'll form several more that will go into the curve. We're going to remember where it crosses the moho, and then we're going to continue on down to the bottom of the model. So I can just do that all at once. Okay, so we've created those. You can look at the vertices that you've created. Those are all the ones that went into the topography and bathymetry. And then we have these that are down here forming the subduction interface. If you look down here, we also have the ID numbers saved for all of the ones that we care about. So there's one for the trench. So that would be number 13. Oops. and I'm not seeing it up here. And we've created our one curve. All right, so we've created those points for the slab. Now we'll make another spline curve. Okay, so now we have our topography, we have our subduction interface. The next thing we want to do is create the bottom of the slab, and to do that, we're just taking the subduction interface that we created, and we're going to translate it to the east. And so these are vertex IDs that we've saved. So we're going to take those vertices and copy them, and then move them 120 kilometers in the positive x direction. And then so there are those. And then we're going to create a couple of extra vertices to finish out the bottom of the slab there. Okay, so there are the two new vertices that we created. And then we're just going to make a spline curve out of that set of vertices. So there we go. So we have our three main interfaces now. We're still going to need to put our continental, the bottom of the crust over here. So we'll have the top of the mantle, put a point there. So we created this point, and then we're going to just draw another spline curve across. There we go. So that's all of the interior geometry for our problem. We're going to have to put outer boundaries on it so that we can mesh it. So to do that, we're going to put one vertex at 600 kilometers and minus 340. There we go down there. So then we'll draw a curve using that. Oh, we didn't use that. That was one over on this side. So this will be slab bottom. We've drawn the bottom now. Now we'll draw the eastern boundary. Okay. So we have all of these curves that we've created now. So now we're going to split these curves into separate segments so that we can create bounding surfaces that use these curves. So the first one we're going to split is the topography bathymetry curve. And we want to split it where it crosses the top of the slab. So we're going to split it right there. And that will allow us to have a bounding curve on top of this region here and another one on top of this region here. So if you look now, this is split into two curves. We're going to do a similar thing with the top of the slab where it crosses the continental moho. So we're going to split it right at this point right here. Okay, now we split it into this part and this part. Similarly, we're going to split the western edge where it hits the continental moho. Okay, this part. Then we're going to do something similar with these other two, so I'll just go ahead and do those. So now we've broken all of our curves so that each of the separate regions in here is now bounded by a set of curved segments. And so then what we're going to do is use these segments to bound different surfaces. So we're first going to do the continental crust, which will be bounded by the topography bathymetry curve, the western edge, the continental moho, and then slab top at A, which is when you split something, it'll somewhat arbitrarily, when you split something into two, one of them will get an at and then a letter designation. So this slab top at A is this right here. So we're going to make a surface out of those bounding curves, and then we're going to give it the name continental crust or concrust. Okay, so there's our first surface that we've created. We're going to do the same thing for the continental mantle, bounded by the continental moho, the western edge at A, and then the slab top. This will be a triangular region. There we go. You'll notice it doesn't always match up perfectly with the where the curves are, but it's actually done it correctly. Okay, we're going to do the same thing now for the oceanic crust. It's going to have, let's see, 6 different bounding curves. And so there we are with the oceanic crust. Similar thing for the oceanic mantle. So that's all of the surfaces that we need for our problem. Now, once you've done that, you don't need the vertices anymore because we've already made our surfaces, so we can get rid of all those. And And then we need to imprint, which is Qubit's way of letting one surface or volume know that it's connected to another one on the other side. So we'll first do that. Okay, once you've done that, then you can do a merge, which is where you collapse together coincident curves, vertices, etc. So we'll merge everything. There we go. So let's see what it merged. Yep. It merged together 4 curves. Okay, then you need to do what we're doing with this particular problem. You have to use the stitch command, which stitches together all of these surfaces and makes a volume out of them. So we're going to go ahead and do that. Okay, now it's made it a single volume. Volume 5. Okay, then we're going to split the top of the slab surface. So you can, we're going to split it 80 kilometers from the end of it. So there you can see we've split it into, let's see, yeah, this is the part we split up. And then we're going to also split the topography and bathymetry so that it'll have a similar looking split as the fault surface. So here we've split this. And then we're going to split the bottom of the slab as well. So you can see the different chunks that we've divided these curves into. And what that's going to allow us to do is to give different types of discretization sizing information along the different curve boundaries, curve segments. So we just finished doing our geometry. So now, if we go back to the main meshing part, we're going to use triangles to mesh this because, especially in things like this where you have, say, sharp corners, it's going to be a lot easier to mesh that with triangles than it would with quadrilaterals. So we're going to tell it we want to use a tri-mesh meshing scheme, default scheme for all of the curves. And then we're going to tell it that there's no sizing function information along any of the surfaces. Okay. So the first thing we're going to do, we're going to, again, we're using the FFPro editor here. We're setting an 8-kilometer kind of base discretization size. That'll be our smallest resolution. And then in Qubit, you can have what they call a bias curve, where you can bias the resolution from one end of the curve to the other. And there are different ways of doing this, but one of them is to use a bias factor, which is kind of the factor by which the size increases. So what you can do, we're going to have a bias factor of 1.2. We'll go ahead and set those. Okay. So now for some of these, we're just going to have a constant discretization size. So we're going to do that for slab top at A, for the topography curve, and for slab bot at C. So we can see which ones those are. Let's see. I think that was one of them. Slab top at A. So that's going to be constant 8-kilometer discretization size. We're going to do the same for topography bathymetry, which is going to be 8. That's that part right there. And then that's slab bot at C. So this one, and this one. We're going to just give it an 8-kilometer resolution. Now, if you want to see what you have so far, you can use the preview command. So that shows you what your specified discretization is so far. So you can see we've got reasonably fine discretization on these curves, and pretty much they're very coarse on the rest, but we're going to finish specifying it now. So now, on some of these other curves, we're going to give it a bias factor. We're going to say that the finest size is dx, which we've set up here. We're going to tell it what's the starting vertex is. So for this curve, this is topography at B. Let's see, which file is that? That's this one right here. So this curve, if we look at it, we can see vertex 75 is this one that's closest in. So starting here, we're going to increase the size as we move further away from there by a factor of 1.2. So if we do that, now let's look at what it looks like now. So you can see what we've done. We've started with the fine discretization size right here, and then it's increasing by a factor of 1.2 each time as we move towards the edge of the mesh. So we're going to do similar things with some of our other curves. We'll do it, let's see, there's, this will be this one over here, I believe. And as well as this one, that one. So let's do it for those. So we'll do it for all of these. Okay, so now you can see what we've done is we've got a mesh that's finely graded in the middle and then gets coarser as we move out towards the edges. We haven't quite finished. So, and on the boundaries, we're just going to use a constant size of 50 kilometers.
So you're going to need to go a little faster if you want to get things.
All right, okay. I couldn't remember how long this was supposed to go. Okay. Well, anyway, so we're essentially done. We've already told it a triangular mesh. We've got our discretization size, so we'll just mesh it up. And there we go. The only other remaining part, really, we can smooth it to get better element quality. Okay, and then you can see what the quality is. Okay, and you see it's pretty decent quality. 2 is what you aim for, but okay, I'll go ahead and finish up here. And then the last part is the boundary conditions. So the first thing we do is create blocks for all of our different materials. So we have all these different surfaces that will correspond to the different materials. So all we have to do for that, associate the surface with the block number. Okay, so we've done that. If you go up to your, you'll see that we now have all these blocks. We have the continental crust, continental mantle, oceanic crust, and the oceanic mantle. And then you do a similar thing for node sets. So the first thing we do is we use groups so that we can do logical operations on the node sets. And then once we have the group that we want, then we form a node set out of those. So we're going to form the coseismic part by adding the node in slab top at A, which is that right there. And slab top at B. So that'll be double that one right there. Yep. Okay. So we form our group, give it a name, and so so now we have this group right there. And now that's the nodes that we want, so we'll just put those in a node set. And that's what will be exported in the XDIS file. Okay, so have a node set. There we go. All right. So we're going to do similar things for the slab bottom. And then we'll go ahead and just do it for the rest of the fault. And now we've created those node sets. And then this is for what we call the ground surface. This is just the whole upper surface of the mesh. Okay. So that's that. And then same thing for everywhere we want to apply boundary conditions, we'll do it. So for the western boundary, eastern boundary. And then the mantle we're doing as well. Okay. And then finally, just the bottom. Okay, so that's essentially, that's the 2D subduction zone model where we formed our mesh. We broke a lot of the curves so that we could have different types of discretization variation on them. And then we divided into material blocks, and then finally we defined all these different node sets that we'll need for the finite element model. So are there any questions about that part? So far, no? Okay. What is the schedule? It's, let's see.
We had half an hour for each one.
Okay.
And then half
Well,
an
then
hour.
I'll just launch right into 3D. I don't necessarily need to show the slide that goes with that because we'll see it as we go. So we're done with that one. Let me first the next problem is going to involve a few surfaces, and so what I'm going to do is